My name is Chris Stewart. This is Emily Brunsden, Dr. Emily Brunsden. We are Syzygy. We are the presenters and producers of a podcast that's been going since 2018, which is ridiculous. That's in the pre-times, in the before the COVID times. And it's a podcast about astronomy and all things in the universe. Now, Emily is an actual bona fide astronomer, and I am not. I'm just a science nerd, and so I get to ask all the questions, which then Emily gets to explain why I'm wrong about things and help everyone to understand. That's the general idea. And tonight we're going to be doing, well, Emily's going to be giving a talk, which we are then going to merge into a live episode of the podcast. So basically it's just a talk, but we're recording it and it will be on the podcast. Tonight we are very excited to be talking about exoplanets, planets around other stars. We live on a planet, it goes around a star. Different thing entirely. We're talking about other stars and other planets. Emily's going to explain it all, and at the very end we'll have time for a bit of Q&A. So start putting your questions aside, and we'll get to that at the end. And then the keen-eyed amongst you may have noticed a musical instrument over here, which is my way of wrapping things up in ridiculous style. So that's the next hour. Would you please make very, very welcome Dr. Emily Brunsden.
Well, thank you all. Thank you, Chris. So it's really a pleasure to be part of the Festival of Ideas again. Syzygy have been one of, I think we've come to quite a few festivals now, done lots of different cool stuff. And we're returning to a topic that I think is one of our favourites in terms of looking at finding planets around other stars in our universe. And indeed, there's a version of this talk that I've been giving for quite a few years. I was just saying to Chris, actually, I have to keep updating this talk because the amount of science that keeps coming at us about even the planets that were discovered 10 years ago now is just fantastic. So just before I move on in the slides, I just wanted to point out my badges. I like badges. I've got the University of York as where I work as an astronomer, of course. I'm also the director of Astro Campus, which is the observatory here at the university. It's free to come along and do some night sky observing if you wish to in the wintertime. So ask me about that if you're interested. And also, of course, our lovely podcast, Syzygy, which I do have some postcards, which you're most welcome to take away at the end, because I forget how to spell it, so I understand if you might. But yeah, so today what I want you to do is actually engage not just your scientific critical thinking, but a little bit of your imagination. Because what I want to talk to you about is how we might imagine not just thinking about planets going around other stars, but some very specific, very, very cool planets that we know of that go around other stars. And I want you to imagine what it might be like to go there. And I'm going to start you with just a little bit of a personal story. So when I grew up in New Zealand. Now, those of you who know, New Zealand's a very long way from anything, really. It's even Australia, it's a long way away from, right? So I remember a time when I was about 9 or 10 years old, and my parents, from somewhere, or maybe it came through the door, I don't know where it came from, but there was a travel brochure. And this is going back to the sort of 1990s, and it was all bus trips through Europe. And to me, this was as fantastical as any other fictional work. This idea that you could hop on a bus and go on a multi-day trip around multiple European countries and see ancient Greece, go see the Eiffel Tower in Paris, go see all the, I think there was one about Blarney Castle and going around Ireland. And to me, this was just outrageous. How, first of all, are you allowed to even go from one country to another country without getting on an aeroplane? Like, seriously, was that allowed? But it was just also fantastical, and all this history and all these different stories that came with that. And so I want you to try and think about maybe times when you've thought about the fantastical nature, the anticipation of perhaps travel, and tap into that, because that's kind of where I want you to think when we're going to some of these wonderful places that we have in our own galaxy. So this is my welcome to you, all of your cosmic travelers. And if you like, I can be your, I would say tour guide, but actually it's going to be a little bit more like a sales pitch here. And as we tour through, I do want to highlight a couple of disclaimers. The first one is, I'm sorry, but I'm not responsible for any alien encounters, whether they're friendly or not. But I'm also going to tell you a little bit about science, about what we're doing as we go along as well. Now, when we talk about doing something that's thinking about places that are so incredibly distant, I mean, I'm going to tell you some numbers about how far away some of these places are, but let's be honest, they're not going to mean much, because a big number is a big number, whether it's a little big number or a big, big number. So in some senses, it's not really going to matter how far away these places are, they're just a long way away. But then it comes to the point of why should we actually be doing this? Why should we look for exoplanets? And I have a few kind of questions that I personally would like answered by the field of exoplanet science. And these are mine. You can tell me if you relate to them. I'm interested in how many worlds there might be out there. I'm interested in asking, is Earth special? Is it the only? Are we the only one? Or is it just a normal planet? Are there lots of us that are very similar? What kinds of planets might there be out there in our galaxy? Are they all, as I say, like Earth, or are they different? Are solar systems like ours, so sets of planets, we've got 8 planets in our solar system. Is that normal? Or are we special? What makes a planet habitable? Could there be life on other planets even? Or could we survive on another planet? Those are two very different but very interesting questions. And it all sort of then comes to, how did we get here? How did life arise therefore on Earth? And the big, big one, you might arguably even say one of the biggest questions that science is currently tackling. Are we actually alone in the universe? Are we the only bit of life that there is? Either way, if you know the answer to that question, either way, the answer is fundamental, I think, to understanding us as humans. So if you're not interested in any of those questions, I'm sorry, this talk probably isn't the right one for you. But if you're interested even a little bit in even one of them, then you might get a little bit of something out of what I'm going to say. I'm left looking like this, really, to be quite honest, when you think about those questions. They get very big very quickly, and so I feel a little bit overwhelmed by it all. But it is a wonderful time, and it's a wonderful time we're living in where we can actually, you can almost touch the idea that we might be able to answer some of these questions in the very near future. Now, the other thing I wanted to say today is that exoplanet science suffers a little bit from its own publicity. It's cool, it's sexy, it's exciting. That does mean that there's a lot of media that's generated about exoplanet science, which is good. But there's also a lot of mixing up, I would say, between the art and the science. And I'm going to show you a lot of artwork today about what some exoplanets might be like. But I'm also going to tell you there's only one picture of an exoplanet in this entire talk. So your challenge is to see if you can spot it as we go through. It makes sense to start talking about planets by thinking about our own little planet, our planet Earth. This is our little place in space, or our oasis even in space. It's the only planet we know that has life in it. It's the only planet we know to be habitable to human beings. So this question of what is a habitable exoplanet is not something I'm afraid I'm going to answer in the next 20, 30 minutes. It's not even something that I teach an astrobiology course at the university that goes for 20 lectures of 2 hours each with colleagues from biology and planetary science experts as well. We don't even get to the crux of this in that length of time, so I'm not going to tell you the answer. But I can tell you some of the things we might be looking for. So one of the things you might think of when you go out there to find habitable places in the universe is actually we've got a sample of one. We know that the Earth has life. So perhaps the easiest thing to do is to go out and look for something that looks like Earth. Now, there may well be life in kind of silicon forms, in all these other sort of weird and wonderful ways that you can dream up in science fiction. But they're quite difficult to understand because we don't have a local example to study here on Earth. So we're kind of, in exoplanet science, we're doing the easy stuff first. We're going for things often that really look like our own planet Earth. And so on the following slides, I'm going to give you some data. Now, don't worry if you can't read it all. The numbers are there largely to prompt me as well, because I don't remember the stats about every single exoplanet. But these are some of the things that we might be interested when we look at a planet to see if it might be habitable. We might want to look at its mass. So here's an example for the Earth. Our Earth is 1 Earth mass. Makes sense? I know. As I say, we're doing things easy tonight, right? Our planet Earth also has 1 Earth radius. You might be surprised to also find out. Now, I'm going to talk about stars and their temperatures a little bit. So I'm going to ground this and talk about them in terms of Celsius, degrees Celsius. Our particular star, the sun, has a surface temperature of about 6,000 degrees Celsius. And our planet temperature is about 15 degrees Celsius on average, which is actually not terribly different to what we experience today, right? So we just have a little bit average. Now, also when I talk about distances, I'm going to give you some distances in a measurement unit called light years. A light year is a distance, although it sounds like it's a time. It's a distance. It's how far light, the fastest thing there is, can travel in an entire year's worth of time. It's a long way, basically. That's really all you need to know. It's a really long way. But if you want a sense of scale, the sun to the Earth, the light takes 8 minutes to go from the sun to the Earth. So when I talk about a year, that's obviously a lot further than our sun. So I'm going to give you some of these stats for some of my favourite planets. But I'm going to start basically from the very beginning. And I'm going to tell you, actually, the first thing that we knew about exoplanet science was that even the very, very first exoplanets we found were utterly bonkers. Completely strange. Nothing like what we expected to find, nothing like what we had seen even in our own solar system. And this postcard here from the NASA, these pictures I'm going to show you all from the NASA Travel Bureau. And what they put together was a whole series of travel posters. And this one here represents some of the first exoplanets that we found. And I'm going to talk about 51 Pegasus B, 51 Pegasi B, which was found in 1995. And this was the first exoplanet that was found around, let's call it a normal star, like a thing that you might recognize to be a star. And this planet here has some statistics. We can look at them. It's about half the mass of Jupiter, so it's kind of okay, similar, maybe a bit bigger than Saturn. About twice the radius of Jupiter. The star's temperature is 5,000 and a bit Celsius. That's not too dissimilar from our own sun. Now the next one is where it gets interesting. The temperature of this planet is 1,200 degrees Celsius. And the reason is because this is not a planet that's at the same sort of distance as Earth from the sun. It's closer. It's closer to its star than Venus is to our sun. It's closer than Mercury is to our sun by quite a ways. In fact, it is so close, it's only about 10% the distance from our sun to Mercury. So this is a really big, puffy, gassy giant, like you might imagine Jupiter or Saturn, snuggled in really close to the star, which makes it incredibly hot. So it's actually not a fantastic planet to be going and finding life. But the reason why it was bonkers, completely bonkers, through everybody to begin with, was that Jupiter and Saturn, our big gas giants, even Uranus and Neptune, they form out of a lot of gas. And we understand why they live and where they live in our solar system. And it's because they form way out in our solar system, beyond the point where water freezes. And that means that they can gather up all this hydrogen and helium, become these big gas giants, right? You can't do that if you're in the inner solar system, where you've got Mars, Mercury, etc. We're all little rocky things. Big gassy things far away, little rocky things close to stars. That's where they form. So that when the first planet that we find is a big gassy thing, but right next to its star, that's a bit crazy. We're a little bit perplexed. Already our models of how solar systems are formed are almost instantly broken, or at least challenged. Now, we do have some good understanding of how these planets might form today, but to be the first one, to be such a weird one, was just very, very surprising. And from that point onwards, I'll tell you, exoplanet science has not gotten any more normal since. Everything is bizarre and weird, and in a wonderful way, because it tells us something about all those questions that I put up on the earlier slide. Now, if you want to travel to this exoplanet, so putting my travel host hat on, let's say, I did do some calculations. I'm a maths nerd, I'll be honest. Did some calculations, and I took the idea that if you might drive your car to an exoplanet, I mean, don't, it's not a good idea, but it'll take you a really long time. But if you did, how much fuel would you do? And that's kind of a proxy for how much maybe this holiday is going to cost. So if you were to drive your car to this exoplanet, and assuming something like 70 miles per gallon in efficiency at today's fuel prices, which these are 2026 updated prices, it's going to cost you something like 15 trillion pounds to go to this exoplanet. You can get your bank cards ready if you want. I'm happy, I'll take all forms of payment. Now, the reason, again, I'm putting this up here is just to give you a little bit of a hook to say, well, this is 15 trillion pounds, so you can get a little bit of a sense when I talk about other ones, whether or not they're more or less expensive. So if you want to go and see the OG exoplanet, let's call it, the original, then you're going to have to fork out about 15 trillion to go see a very hot Jupiter-like thing going around its star at just 10% the distance of Mercury. 4 days it takes to go around. It's super quick. The closer you are to your star, the faster you go around. 4 days. So you're going to age really badly on this exoplanet. A year is 4 days long. So you're going to be quite old when you come back. Now, how did we find this exoplanet? It turns out we used a really, really special trick. Exoplanets don't produce their own light. By nature, they're planets, whereas stars are the things that make the light. So the stars are the things that we see. And pretty much in all exoplanet science, what we are looking for is actually not to go out and directly see the planets, but we go and look for signatures of the star that mean that that star has got an exoplanet. So there's an old adage in our field, which is know thy star, know thy planet. So we look at changes of the star to then say that it's got a planet. And this was the technique that was used for this particular planet. This is actually a really cool technique. It turns out when something is orbiting another body, you don't get just the tug of the smaller thing, or the bigger thing on the smaller thing, causing it to orbit. In this case, the star is tugging on the planet. But that planet also tugs on its star. And so even the Earth will cause the sun to wobble just a little bit as we go around in our own orbit. Now, the bigger you are, the more massive you are, the more you tug, the more you wobble. And we detect these wobbles not because we actually see the stars twinkling and wobbling, but actually we see the colours of these stars slightly change. And this is what this animation is showing you. So at some points in the orbit, you see the light becomes a little bit redder. And at some points, as that planet goes around the star, the light becomes a little bit bluer. So this is what we call Doppler shift. So the colour of the star changes a little bit. It goes a little bit redder, then a little bit bluer, then a little bit redder, and a little bit bluer. And we measure that, and we measure that colour change, and that is how we know that that star is wobbling because it's got a planet that we can't see going around it, which is pretty incredible. It's even more incredible when I tell you what we're doing this down to a detection limit. The velocity of that planet wobbling is about 1 metre per second. So the surface of that star is moving a metre in a second, tens of light years away, and we're able to detect that with our instruments here on Earth. Isn't that incredible? A metre per second. And there are people who are working right now on not just detecting these planets at a metre per second, but a centimetre per second. Surface of the star, I know, it's outrageous, isn't it? But this is where we are. I mean, this is how we detect these planets. Now, these hot planets are actually also in themselves bonkers, right? They shouldn't have formed. Well, in fact, we know that they didn't really probably form where they are now because the way that solar systems form just doesn't work that way. But I wanted to put up this next planet just to show you a little bit why these planets are so weird. This is 55 Cancri E. It's a little bit more like an Earth-like planet. And we can look at its stats. This one's about 8 times the mass of Earth, so it's not a Jupiter-sized thing. It's kind of a rocky-ish thing, about twice the radius of Earth. And so it's much more Earth-like, we think. Now, the problem is this one is breaking even more of these records about being weird and crazy exoplanets, because this one is not going around its star in 4 days, like 51 Pig. It's going around its star in 18 hours. It does a whole loop of its star in 18 hours. It's incredibly close, almost star grazing, what we call this planet going around super, super close, which means that if it's a rocky thing and you take a rocky lump and you stick it next to a star, guess what's going to happen? It's going to melt. So we think that this planet may well have a surface which is just basically lava. Now, my son really likes playing a game called The Floor is Lava. Can you imagine his mind blowing when I told him the planet was lava? You can't win, I'm afraid, in this game. But it's a wonderful example of just the extremes that we're seeing in exoplanet science, these bizarre worlds. In fact, very recent measurements of this planet actually says maybe it's not got a rockiness that's made up of silicates and things like the Earth is made up of granites and silicates and things like that. Actually, this planet might be made up of carbon, lots of carbon. Now, because it's very big, it squishes the carbon in its core down to something very, very, very high density. And does anyone know what high density carbon does? See, some people are looking really excited now. Yeah? Diamond, well done, yes. So there's good-ish evidence that this planet, maybe the inner third of it, might actually, the core, be diamond under extreme temperature and pressure. Amazing, amazing. A whole planet, well, at least a third of a planet made up of diamond. But you've got to get past the lava first. So, you know, we'll figure that one out. So if you want to go and I would say see the diamonds, but you're not really going to see the diamonds. If you want to see the world that maybe has a diamond core, it's about 41 light years away. And so in terms of a holiday cost, it's actually fairly similar to the last one. It's only about 12 trillion pounds, this one. No? Any takers? No? Maybe the floor is lava game put you off a little bit, that one.
If you got the diamond, that would probably pay for a trip.
That's true, yeah, exactly. Can you imagine how big a diamond that would be? Well, you flood the market, and I don't know, economics, something. Anyway, so I mentioned from the previous exoplanet that we detected it using these color changes of the light. That's actually not how we found most of the planets that we found today. We found about a third of them in that method, but between them, these two heroes of science have actually detected around about sort of 50 to 60% of all the planets we know. And they use a very different technique. So these are two space telescopes, Kepler, which did its main mission from 2009 to 2013, and TESS, which is currently flying and has been since 2018. Now these are space telescopes, so they're above Earth's atmosphere. They don't have to deal with, I know you can't see, but I can see, the grey, grim clouds that are out there, right? They don't have to deal with the fact there's day and night. They just go up into space and they just observe. And for example, Kepler stared at the same patch of sky for 4 years. Now, there's no astronomer on Earth who's going to spend 4 years uninterrupted staring at the same patch of sky. But good things we've got robot telescopes in space who'll do it for us. And what these telescopes are looking for was something slightly different. Again, it's something about the star. We're looking for how the star changes, but this time it's a more straightforward measurement. For these telescopes, we're looking at how the brightness of stars change. And what we're thinking is that when you see the brightness of a star dim just a little bit, then what we're seeing is that we've got such a perfect alignment that there's a planet that's traveling in between us and that very distant star. As it does so, it's called a transit. It blocks a little bit of the light from the star. You might have heard of transits that we see in our own solar system, the transit of Mercury, the transit of Venus. This happens where those planets get in the way of our sun, we get a little bit of dimming, and this is the same phenomenon, just a lot further away again. Now I told you about that meter per second, that centimeter per second that we were looking at for those other ones. For this one, I'll let that video hopefully go again so you can see it. We are looking at detections in the change of light, so we're measuring how bright the star is, and we're watching its brightness drop by less than 1%. So that's why we needed these fabulous telescopes up in space, away from the grey Yorkshire clouds, away from the light from the sun, to be able to detect these super, super tiny measurements of these these little dimmings, 1% drops or less. We're getting down to, with our best telescopes now, something like 1/10 of a percent in those drops. Just incredible. And what these two telescopes have told us is actually we're not just living in a galaxy that's filled with planets that are so close to their host star that they're lava and gassy and hot and things. We found planets that are kind of much more normal. And the first ones we found are these ones called super Earths. So in our solar system, if you sort of line up all our little planets in order of size, then you've got the Earth, and then the next one, as you get bigger, is Neptune. Right? Neptune's about 4 times bigger in radius. than the Earth. Now, it turns out that there are a lot of planets that are in between the Earth and Neptune. Some of them are called super Earths, so just a bit bigger than Earths. Some of them are called mini Neptunes. We're not always as creative as we'd like to be in astronomy. We just put them in the middle. And this is one of them. And I like this exoplanet because it tells us something about, when we think about what it's like to be there, what does it mean to be on one of these super Earths? So this particular one here, it's about 2 and a bit times the radius of the Earth, about 8 times the mass. So it's, somewhere in that middle between Earth and Neptune. But because it's got more mass than our Earth, what happens is the gravity is stronger. So on this particular planet, the gravity is about 1.5 times the gravity that we experience on Earth. So if you think getting up in the morning is difficult on Earth, it's going to be 50% harder again to do so on these super Earth exoplanets. So you're going to feel this kind of crushing gravity. Every step is going to be this enormous amount of effort. If you fall over, you're going to really hurt yourself because of the gravity is so strong. Or if you're into very extreme sports like, I don't know, skydiving, then having more gravity maybe pumps up that adrenaline level even higher. It's not my thing, but because this planet is relatively close, at just a few tens of light years away, you might be able to go along and try these extreme sports for, again, only about 12 trillion pounds. Just a nice easy summer holiday. I'm sure there's lots of extreme sports, by the way, that would benefit from more gravity, or at least make it a lot more exciting than it even is on Earth. So these super Earths, it turns out these super Earths are so common in our galaxy that I'm almost left thinking, why did we miss out in our solar system? So here's a sort of a schematic. We've got the Earth at the top, we've got Neptune at the bottom, and the white thing, it's white because we don't really know much about it. It's just, here's a circle that's in between. These are our super Earth-sized exoplanets. And the shocking thing is, when we went out and looked with Kepler and with TESS, we found out that actually, if you would take all the exoplanets that you can find in our galaxy, you get quite a lot that are Earth-sized. You get very few, actually, of these big gas giants. They're not so common after all. We're good at finding them because they're big, but there's not many of them in the whole general population of exoplanets. What is incredibly common are these super Earths, so these things that are kind of in between Earth and Neptune. In fact, they are the most common size of exoplanet that exists in our galaxy. And now I'm starting to feel really shortchanged because we missed out in our solar system. We don't have one. Why? We don't exactly know, but something about our solar system means that we don't have this super Earth. And what's also quite a little bit frustrating is we know what an Earth looks like. We have some ideas of what a Neptune looks like. We've sent probes, right, to Neptune. But we don't really know what a super Earth looks like. Is it a rock with some atmosphere? Is it mostly atmosphere and only a little bit of rock? Is it ice, like one of the moons of Saturn or Jupiter? We just don't know, right? All we measure with these exoplanets is their size, so how big they are, and their mass. And that means that there's actually, you can make the same exoplanet lots of different ways. You can make it with big cores, little cores, big atmospheres, little atmospheres, and still have a solution that works with your measurements. And this is one of the tricky things about exoplanets, is actually figuring out what they are made of. So it would be remiss of me to talk about exoplanets without doing at least a little nod then to the science fiction. Because as in lots of places in science nowadays, science fiction led the discoveries in a sense. So we had these ideas that these types of planets might exist in fiction before we went and found them. And this is probably one of the most famous examples of that. This is Kepler 16b, which when it was discovered was instantly renamed to being Tatooine. And the reason why it's been renamed as Tatooine, if you're not a Star Wars fan, is because this planet is not going around one single star, but it's going around what we call a binary, a pair of stars. So there's two stars going around each other. They were born together, they live together. They're very happy going around each other. There's no issues. Hopefully. No, they'll sit there for millions of years. They're absolutely fine. But there's a planet then going around. Yeah, I'll show you a video in a minute. I don't have enough arms to do all the orbital mechanics here. So there's two stars. So there's one that's 4,700 Celsius, one that's a bit cooler at 3,300 Celsius. Now, this planet, despite NASA's wonderful travel brochures that tell you, let's go and see this, double sun in the sky planet. The problem is this planet is actually a bit of a Jupiter. So the picture is a little bit of a misnomer. You're not going to be able to stand on the surface of this planet. It's a big gas giant. It's about a third the mass of Jupiter, about 2 and a bit times the radius. The planet's also very, very cold. So it's a little bit further from its host star, so it's a little bit colder. It's not going to be actually the nicest place. So this particular image here is actually an imagined moon. Now, we haven't found any moons around other planets other than those in our solar system. But you might hypothesize if there's planets, then surely some of them must have moons. And that's the idea here. So maybe there's a nice moon on this big gas giant that you can stand on and take your wonderful selfies with the double sunset of Tatooine. But if the orbital mechanics of my hands was not sufficient for you, I do have a nice little video that shows this. So this is our gas giant here, the planet. And there's our little star system. So you've got 2 stars, one big, one little, one bit yellower, one a bit redder, going around. And then that planet is going around both of them. So in the sky, in this particular example, you would always see those stars quite close to each other in the sky. You wouldn't sort of get them too far away because the stars themselves are quite close. But it's a very cool thing to imagine, isn't it? Going and seeing a double sunset. That sounds amazing. So let's come back down to our habitable idea. Kepler 186f was, when it was discovered, deemed to be, actually, it still does hold the record. It was the very first Earth-like planet found in what we call the habitable zone. So this is at a nice distance from its star. You might have heard it as the Goldilocks zone because it's not too hot, it's not too cold, it's just nice and warm. Basically what we mean by warm is where liquid water would hypothetically exist if water is there, which may or may not be. But nonetheless, so first planet that we found in this habitable zone that's kind of Earth-like in size. In fact, it's a bit smaller than the Earth, a little bit less mass than the Earth, slightly bigger in terms of radius, slightly less in mass, which probably means it has a little bit more atmosphere, but that's okay. Star's temperature is a little bit cooler than our sun. The planet's a bit cold, so you might need a couple of jumpers to go to minus 85 Celsius. But that's okay. Now, what's really interesting about this planet was because it was the first one discovered, we started, of course, to think, what would life be like on this planet? Now, that star temperature of 4,100 degrees, remember our sun is 6,000 and a bit, right? So it's only like 2/3 as hot as our sun. And what that means is actually this planet would only receive about 1/3 of the energy that our Earth receives from our sun, from its host star. So less energy, and more of that energy is going to be towards the infrared part of the spectrum, so red-coloured light. So as you might see from the poster, you could then hypothesize of how would life adapt to such an environment. Less energy and more red light. Well, I'm not a biologist, but I'm told that this is a potential adaptation route, is that actually what you could have as your plant life, for example, instead of being green, which is the kind of output of the sun, we have most of it, the sun's light actually comes out in the green colour of the spectrum. But actually you might have more like red plants in this particular world, adapting to the different starlight that this particular place has. So from this beautiful image, you can imagine red grass, red trees, red ferns, I don't know, whatever, red things. I think it'd be very cool. But unfortunately, if you want to go and look over the picket fence into the red lawn, that's a bit more manicured than your own, this is actually a very, very distant exoplanet, and it's about 490 light years away, or therefore a holiday cost of about 140 trillion pounds. Very exclusive, I'm told, this one, yeah. So yeah, it is quite far away, but it was a very, very exciting find. And again, we're thinking about what these places might then be like. And then it would be, of course, remiss of me to talk about exoplanets and not talk about this one, the most famous set of exoplanets, I think, that we have found, because we are so excited about these exoplanets. This is the TRAPPIST-1 system. Now, this is not just one exoplanet. This is a set of 7 exoplanets, so a whole system of exoplanets going around a star where all 7 of those planets are basically the same size as Earth. And this is very, very cool, because it means that if we were to go there, then there's not just one chance of there being a habitable environment in this system, there's 7 of them. I mean, some of them have got to be nice at some point, right? So the planets' masses, they range, but there's sort of a little bit less than the Earth to just a little bit more, same with the radii. Now, the problem is that these exoplanets are very, very close to their star, which means that the star is very cool. So some of them do fall into this habitable zone where we think liquid water could exist, but they're all 7 of them are huddled well within the orbit of Mercury into sort of comparison to our own solar system. So they're very, very close to their host star. Really, really cool star, only 2,600 degrees. That's almost not a star at all. I mean, it really only just made it up into the star category. Before that, you don't have nuclear fusion. So this star only just scraped it in. But it scraped it in and got 7 exoplanets, so we're championing this one. Now, TRAPPIST-1e, so we've got B, C, D, E, F, G, H. Yes, we've got 7 of them. So we've got, E is the favourite. So if you're a betting person, E is the one with the lowest odds for having life. It's in the middle of the habitable zone, and so far we haven't proved it doesn't have an atmosphere. B and C don't. We have measured those to not have an atmosphere. E, the jury's still out. Measurements are inconclusive yet. But we're trying really hard because this is a really close system as well. We're very lucky, so we can get more detailed measurements from this system. So the idea with travel to this system is that it's not really traveling to one place. You could planet hop around all these little planets and just go to the next one. If you're a bit hot one day, oh yeah, we'll just go a little bit further out, have a little bit of an ice bath over there on planet H. Oh, it's getting a bit cold, we'll snuggle into the sauna on planet C. I quite like this idea. It could be like a spa. Oh, I'm going to go to the spa system. Right, the Swedish spa system. I'm going for it. Right, but anyway, the idea is that at least some of these planets, if they have water, it's got to be liquid somewhere, is the idea. Now, this will only cost you about £12 trillion to go to my spa system. I think that's a bargain, to be honest. You've seen what the spas cost these days. When you get 7 of them to play on. So that's really fun. And if you want to see an idea of how this whole thing works as a system, this is a nice little animation of all those orbits together. And then you're going to see, just coming up at the bottom, how we detected them. Because, of course, there wasn't just one drop in the light from the star as the planet moved in front. We got lots and lots and lots of these little drops as each of the different planets came and went. So here they are now. They're slightly passing in front of their host star, and you get these little dips. So there's C, B. Now, I reckon you could turn this into a nice song, Chris. Yeah. I mean, those are all notes, right? Musical notes. Yeah. Can you imagine
H
playing
isn't a note, but we'll work with that.
Yeah. So this is the kind of measurements that we're making of these exoplanets, seeing with lots and lots of planets, seeing them just go around and around and around and around. And it's beautiful. I mean, it is. It is truly beautiful. So the last exoplanet that I wanted to talk about today is something that I think, again, is bonkers, but it broke the rules once again. Now, there's this idea that a exoplanet is a planet that is going around a star that is not our sun, right? That would be an easy definition of what an exoplanet is. Planet just around a different star. However, it didn't take us all that long to start finding planets that didn't have a star at all. So this is what we call a rogue planet. So it's got no star. This is its wonderful name, PSOJ 318.5-22. And it's It's a fairly big exoplanet, so it's about 6.5 times the mass of Jupiter, 1.5 times its radius. Doesn't have a star, so we don't have a star temperature.
Emily, I like the way that you've got rouge planets there. I thought we were going for a different colour.
Rouge.
Yeah, doesn't matter.
Anyway.
Carry on.
All right. Yeah, our rouge planets,
Yes.
because they're quite, because look, I mean, they're partying. You've got to put your rouge on to, I don't know. I'll let it go. Yeah. Anyway, we've got this thing. So in this case, of course, it's a gas giant. It's something a few times the mass of Jupiter. It's a big, puffy, gassy thing that's just floating around in space with no star. So this particular image of this travel brochure is actually imagining that this planet might have rings, and maybe we can dance along the rings. Now I think we're getting a little bit tenuous here. But the idea is that the party would never end. I mean, you think New York is the city that never sleeps. Well, you never have any daylight at all on a planet like this because there's no host star at all. It's about 80 light years away. So if you're really a really good party person and you want to do your clubbing 24/7, quite literally, this is going to cost a little bit more to go to this sort of free-floating ball out in there in the galaxy. It's going to cost something like 24 trillion pounds. But, you can pack a nice big suitcase full of all your outfits. Lots of glow-in-the-dark wouldn't work because there's nothing to charge it. Anyway, we'll get there. These rogue planets. Now, I've got this lovely little movie that sort of, I think, encapsulates a little bit of the isolation of these planets. They really are completely dissociated from other stars in our galaxy. And we don't think these are just one-off planets. We actually think there are probably hundreds, thousands, maybe even millions of these exoplanets in our galaxy. That are just floating out there, disassociated from stars. And of course, if you don't have a star, but wait, Emily, you told me just before, we find exoplanets by looking for the signatures from their stars. We look at those colour changes, or we look at these little dips in brightness as they transit. We can also take pictures of them. Ta-da! That is 12 pixels of magic of a planet that we have taken a direct image of. There's only a few planets that we have been able to take a picture of today's number, 6,298. That's 7 more than Tuesday, when we last spoke in Syzygy. But there's just a handful, but this is one of them. So those are your 12 pixels. Now, you might be disappointed, given all the other lovely pictures I've been showing you, the artwork, the imagination stuff. But I actually think this is fantastic. I mean, to be able to take a picture of something tens of light years away as an exoplanet, it's not going around a star at all. But I think this is completely incredible. It's amazing. So, what, therefore, might be next? It's not that. I pick this image every time because this is imagining what it's like picture that's just complete fantasy. There's nothing in this picture of what the surface of an exoplanet would look like that comes from science or reality. We don't have the measurements. We can't tell you if an exoplanet has oceans on it, if it has an atmosphere, if it has islands, if it has fish, if it has icebergs, whatever. Those are beyond our current capabilities to measure. But there are some places, some worlds that we are getting tantalizingly close to making some of these measurements. But that one is just nonsense. So, what is the hero of the moment that we're going to have to come and make these measurements, to find out actually what really these planets might be like? I mean, maybe I should have left the music on for this one. It's so dramatic. I mean, there's one thing that NASA and ESA do incredibly well, and it's self-promotion. This is the James Webb Space Telescope. So it's sitting out there. You get to see the underside first, which is beautiful. It's got this enormous sun shield blocking the light and heat from the sun. And as it turns around, you're going to see its 6.5 meter gold mirror. Now, it's not gold because we're just really like exoplanets. It's gold, so it's super reflective. We get lots of light. And what James Webb is doing is something very different to the other space telescopes I mentioned before. Kepler and TESS are out there hunting for planets. They're looking for these tiny dips in light to see if we can find more and more exoplanets. James Webb, amongst other things, is trying to find out what some of these, at least the closer exoplanets, might be like. And this is the kind of thing we're looking for. So what we can do with James Webb, in some cases, in some very, very special cases, is look at the atmospheres of some of these exoplanets. And what we're looking for in the atmosphere, this wonderful graph, is we're looking for the chemical fingerprints of particular atoms and molecules. Every atom and molecule has this kind of chemical signature. You find signatures of it at very specific wavelengths of light that are unique to each of those atoms, each of those molecules. And this is kind of an example, looking at the molecular side. So you'll see these little dips that are coming down, and what you're seeing is those mapped to different molecules, different gases. So here you can see carbon dioxide, ozone, methane, water. And this is what James Webb is looking for on some of these exoplanets. Has it got these chemical signatures? Because first of all, if you're getting some of these gases signatures, then that's a pretty good sign that you've got an atmosphere, first of all, on your exoplanet to work with. And you can tell how much of it is made up of methane, how much of it is made up of oxygen, etc. So you can start seeing what the composition of this atmosphere is. Now, what we hope to do in the future is use information like this to then say, is there life that is somehow changing that atmosphere on that exoplanet? All of these molecules individually can be produced what we call abiotically, basically through like geothermal processes, rocks, gases, volcanoes, whatever, right? Other processes that can happen on these planets can produce these gases. But there are certain ways that you might combine these gases, and certain gases that you might find in different concentrations that mean that your atmosphere is in disequilibrium, or it means that there's life. This is happening on planet Earth, our own atmosphere. If we were able to detect it at a super, super high level of detail, you could tell that there's life on Earth because there is enough disequilibrium, there's bits of the way that the carbon dioxide is balanced with the nitrogen and so on in our atmosphere is unique, at least we understand, to life producing that disequilibrium. Hope one day we might see something similar on an exoplanet, but at the moment, we haven't got those kinds of signatures. We've got signatures that are very tantalizing, that say that we might have atmospheres that could potentially even support life, but we don't have any clear nail in the coffin kind of signatures. Absolutely, there is life there. But we're close. I mean, we are so, so close. It is getting very, very exciting. So of these 6,298 exoplanets that we've found as of today, there are some that we are really, really excited about. This is the Habitable Worlds Catalogue, and this is kind of like a tracker of like these are the places where we really might find life. Now, some of the ones I've talked about today are up here. You might see the TRAPPIST planets are up here. Earth and Mars are the last two if you're looking for sort of a sense of scale. We also talked about Kepler 186f, which is up here, and I think, yeah, that might be all of these ones. There are 29 planets basically up here. 29. So it tells you something about our universe already, that we've gone from 6,000 and a bit down to 29. It tells us that Earths are not super common, right? That actually, even these 29, some of them we know are actually not great candidates for hosting life. They're either too close to their star, they're being blasted by a bit of radiation, they probably don't have atmospheres. So we're not even talking about necessarily finding things that are Earth twins. These are just really the best candidates that we have. And I think from a personal point of view, that's telling me something about our place, our little Earth in space. It's telling us that actually we're quite rare. That even in our best guesses, all these pictures, by the way, the illustrations are nonsense. We don't know anything about the surfaces, the atmospheres, the oceans, whatever of these planets. We're just guessing. But we do know about the Earth and Mars. We do know the Earth is like that. So it tells us, yeah, that we are actually quite special. And so I think as we often do in astronomy, we come full circle. We go out there, we look for the most fantastic, wonderful things that we can out there in the universe. But it often means we then turn around and look at ourselves and understand ourselves a little bit better about how special I think our own little planet is. So that was all I really wanted to tell you. And if you're interested in any of these exoplanets, by the way, and want to travel there, I will have my phone app ready for the paywave. Does anyone have that limit on their paywave? I don't know. But if you are interested in knowing more about some of the other stuff we do, the Astro Campus or Syzygy, we've got postcards, of course, for Syzygy, and there's a QR code there to tell you about Astro Campus, our observatory as well. But I think I would welcome perhaps Chris then to come and help me take some questions.
Well, first of all, huge thank you to Emily. I mean, I think it's well deserved. Very well deserved. So we have time for a few questions. While questions are happening, first of all, if you have a question, please raise your hand. A microphone will come around. We have a fabulous microphone helper over here. Please do wait for the microphone so that we can actually get the recording. You might think, I don't need a microphone. Yes, you do. So, and secondly, I'm going to be setting up, because I'm an egotist and I brought a guitar, I'm going to be setting up while that's happening. And if it means that we need to go over by like 1 or 2 minutes, is that okay? Are we okay with that? That would be fabulous. Okay, who's got the first question? Is there anyone who's got it right up the back? That would be right, wouldn't it? Typical. Back row. All right, first question to Emily.
So I have a question mainly about the rogue planets.
Mm-hmm.
How the hell do they form if they're not around a star?
Really good
brilliant
question.
I've got 2 answers actually. So there's 2 ways. We think the very big ones, like this one, actually formed by themselves. They never had a star of their own. In fact, we don't like to say this to their faces, but we call them failed stars.
That's rude. That's just rude.
They formed the same way as stardust. They are trying very hard. The collapsing cloud of gas and dust is how you form a star. This one just didn't have enough gas and dust to form enough temperature and pressure in its core to start nuclear fusion. So it just kind of, that was it. We do also find some examples of exoplanets that are more like Earth, that are rogue, and we think that those were disrupted sometime in their orbit. So they were merrily going around their host star. They had an interaction with something else massive, perhaps a big gas giant, perhaps another Mars-like object. They got kicked out of their system and then just sent out into space, like some very naughty teenager, I guess. Yeah, so those are the 2 things. Yeah, it's really good.
Very, very quick follow-up question. That's the only one you've taken a picture of.
Yes.
It's a very long way away.
Yes.
How did you know it was there? How did you spot it? That's
we
insane.
didn't know it was there. That's a wonderful thing. So this why it has such a crazy long name is because it's actually a survey name. So it's a Pan-STARRS survey. They were surveying the whole sky, and they just happened to pick this one out. And it glows. I told you that most exoplanets don't glow, but this one glows because it's got a little bit of heat left over from its formation. It's not fusing anything, but it's just sort of cooling down slowly, and that's how we snapped it.
That's just stunning. Right, next question is over here. This person on this side. Wait for the microphone to come across. If you could pass it across, that'd be great. Thank you. All right, what's your question?
Going back to the very first planet you showed that we'd found, it's obviously very large and very close to its star. What's the difference between that and a binary star?
Yeah.
That's a wonderful question. Yeah, so the difference between a big planet going around its star very close, and a binary star is in the binary star, both objects are defined as stars, meaning they're both undergoing nuclear fusion. So they're fusing hydrogen to helium in their cores, lots of temperature and pressure and Even if you took Jupiter and stuck it right next to our sun, it still wouldn't fuse hydrogen to helium. It's not big enough. It doesn't have enough pressure to crush that hydrogen down. So yeah, but the line between what is a big planet and what is a small star is very thin, and
turning that key, trying to get the engine started. It's pretty close. Right?
Yeah. So we're still working on actually where that definition.
How close is Jupiter to being? I mean, would you class Jupiter as a failed star?
No. It's about 13-ish times Jupiter's.
Okay.
So 13 Jupiters plus, you're definitely a star. In like 10 to 13, it's a bit vague. We don't exactly know yet.
Right. Okay. Thank you. Next question. Who's got another question? For those of you who aren't quite comfortable asking a question in this public forum, by the way, Emily has promised to stick around for a little while afterwards outside to take your questions individually. But this gentleman here in the jumper, we have a question.
For planets A and B on that multi-hop one, you said they have no atmosphere, and then you said afterwards with the James Webb Telescope how we're able to detect one. Does that mean we're certain they have no atmosphere, or do you mean with current technology we can't see one, but we might find another way in the future?
Oh, that's good. Certainly to the detection limits of James Webb, which are pretty good, we don't think they've got atmospheres. If they do, they're incredibly thin, like Mercury kind of thin, tiny. They're also very close to their star, so we think the star's just blasting away the atmosphere. It just pushes it off, so they don't have much of a chance anyway. I was more tentative about E because we think it does have an atmosphere, but the measurements we have from James Webb so far are a little bit, we don't quite know how to interpret them yet. So we're, kind of on the edge of what we can do with those atmospheres.
Another question over here. Yep.
Yeah, excuse me. You talked about the giant, it's very odd talking through a microphone. You talked about the giant gas planets that are very near their stars and you don't know how they formed. Would they be captured rogue planets, or have you worked out a way they could form?
Some of them are, but actually we think most of them did a little bit of what we call a migratory dance. So they formed far away from their star, but due to various gravitational interactions, they've kind of migrated in quite close over time.
What sort of thing would do that? Is that like another thing coming nearby and giving it a kick? What's happening?
It's very complex in terms of all the different orbits and the masses that are going on, but there are reasons why solar systems, even our own solar system, has rearranged itself a few times since it formed. So even Jupiter in our solar system has come nearly to the orbit of Mars and then trundled back again. And it's due to Saturn and Jupiter interacting with the Sun. It's once you get more than two masses, you might have heard of the three-body problem. Yeah, it makes my head hurt. It's but that's what the numerical simulations can kind of help us to understand.
And solar systems are weird, right? Like, there's just so much going on. Anyway, listen, we are going to have to call it quits there. But as I said, Emily is going to stick around for a little while afterwards.
Absolutely.
And if it's okay, I'm just gonna squeeze in this song because look, I put a lot of effort into it. Okay, I wrote this when we first did this live back in about 2019 or something. And then I forgot all the words, and so I've had to go and remember them all again. And so you're going to bloody listen to them. I mean, it would be great if you could listen to them. Towards the end, Emily's going to do a little sign off from the podcast, and so when she finishes that, I'll keep playing. But it'd be great if you could just give an enormous cheer as if we're at the O2 Arena, right? That would be make it sound on podcasts like this is huge. Anyway, let's see how this one goes. This is called the Exoplanet song. No, that's starting in the wrong key. Starting C. That's how that goes.
Planet C?
Earth is great. Might even be in my top 8 of all the planets that go around the sun. Might even be my number 1, but I'm not sure. I wanna be stuck here forevermore. So many other worlds to find. Some of them would blow your mind. Not saying I want to move to Mars. Just wanna know what's going down around other stars. I wanna live on an exoplanet. Don't you wanna live on an exoplanet too? Just me and you, having lots of fun on an exoplanet, jumping all around in its lower gravity. Just you and me. I've got my eye on an exoplanet with shimmering rings of ice around it. Moons, so many moons. Moons with their own moons. That's a thing. Moons with their own moons, they're called moons. We did that in episode 19 of Syzygy. It's a real thing. Go and check it out. I want to live on an exoplanet. Don't you want to live on an exoplanet too? Earth has one big, bright, warm, and golden sun. Rises every single morning, sets again each evening. That's boring, 'cause I want 2 or 3 or 4 or even more. Why settle for a single star when a multiple system's better by far? It's good enough for Luke on Tatooine. binary sunset's good enough for me. I want to live on an exoplanet. Don't you want to live on an exoplanet too? Do sing along if you know the words by now. And you, we had us as fun on an exoplanet, jumping up and down in its lower gravity. Just you and me. We'll pick a planet with a much greater mass and have to drag ourselves around on our asses. We just have to lie on the purple grass beneath the bright green sky. Don't know how we'll get there, but it might take a while, because it's roughly 50 billion miles. But when we get there, look around, you'll think that you're delirious. Emily, this star, it's covered in puppies.
What?
Yeah, there's like poodles everywhere.
Oh, it's a dog star.
Serious?
You got to edit that one out, Chris.
Don't like that one, we can try. Rock that's in orbit or at Proxima Centauri. Walking on the sky like glowing sea of lava. Maybe we can meet some of the local exofauna, like fluffy green mice with teeth like piranhas, or giant yellow bats that hang in bunches like bananas, tinkling clouds of tiny crystal butterflies, or pandas that shoot lasers from their eyes. Pandas that shoot pew, pew. Too much?
Yeah. Wrap it up.
I want to live on an exoplanet. Don't you want to live on an exoplanet too? Just me and you. We can have such fun on an exoplanet, jumping all around in its lower gravity. Just you and me, Emily.
I want to give a big thanks to everyone who's come along on their Sunday night to join us for this special live episode during the York Festival of Ideas. And a huge thank you to the festival team making this amazing fortnight of events possible. You can find the Syzygy podcast online at syzygy.fm, syzygy.fm, where all good podcasts are available. The show is produced by Chris Stewart. I'm Emily Brunsden. We'll catch you again soon to explore more of the universe in the next episode of Syzygy.
Oh, big cheer. I want to live on an exoplanet. Don't you want to live on an exoplanet too? Just me and you. We can have such fun on an exoplanet, jumping all around in its lower gravity. Just you and me. I've got my eye on an exoplanet. Let me borrow Kepler and I'll go and scan it. You can come there too. The spaceship's leaving at 2:15. But before we do this planet hopping, it's a long way and we're not stopping. So before we go, I think you should pop into the loo. Loo, 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 loo. Low, 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 shoo-be-doo. Just pop into the loo. Thank you very much for humouring me on that one.
Thank you, Chris.
Emily Brunsden. I've been Chris Stewart. We'll see you online at syzygy.fm. Thank you. Good night.